The human skeleton must solve a mechanical contradiction. It requires absolute rigid shielding to protect our vital organs from blunt force, yet it simultaneously demands dynamic, multi-axial mobility to allow us to navigate physical space. The biological solution to this contradiction is the anatomical joint, or articulation, the precise junction point between two or more bones or cartilages. The structural requirements at these junctions vary. You have the total, rigid simility of the sagittal suture holding the skull together, contrasted with the extreme fluid mobility of the shoulder's ball and socket joint. To achieve both unbreakable stability and free movement across the entire body, medical science classifies every joint based on exactly two structural variables. The first variable is the specific type of physical connective tissue uniting the skeletal segments. The second variable is the presence or complete absence of a dedicated joint cavity. By manipulating just these two variables, the binding material and the internal void, the skeleton generates every necessary degree of human movement. Looking at this diagram, we see the first major classification, the fibrous joint. Here, the bones are united strictly by dense fibrous tissue, and there is absolutely zero negative space, or joint cavity, between them. Because the bones are lashed directly together without a physical gap, movement at these junctions is either entirely nil or extremely slight. This document outlines fibrous joints, starting with skull sutures. It details morphologies based on articulating edges, plain sutures like the internasal, serrate like the sagittal, and denticulate at the lambdoid. It also catalogs complex overlapping connections, the squamous suture and the scindeliosis. The second subtype of the fibrous joint is the syndesmosis. The bones are still connected by fibrous tissue, but across a slightly wider gap using a distinct ligament or interosseous membrane. Clinical examples include the inferior tibiofibular joint in the lower leg or the broad interosseous membrane connecting the radius and ulna in the forearm. This brings us to the final fibrous subtype listed here, the gomphosis. The text defines this as a precise peg and socket architecture. The singular example in the human body is a tooth anchoring directly into the alveolus of the jaw. Across all these subtypes, the structural logic remains consistent. By inherently lacking a cavity, fibrous joints trade mobility for critical structural permanence. The second major structural class is cartilaginous joints. In this configuration, the articulating bones are united strictly by cartilage. Much like the fibrous joints we just examined, cartilaginous joints possess no internal joint cavity. This section of the taxonomy breaks them down into two types, starting with the primary cartilaginous joint, or synchondrosis. These utilize hyaline cartilage as temporary developmental bridges. You see this in the epiphyseal plates of growing bones, or the costochondral joints. The second subtype is the secondary cartilaginous joint, known as a symphysis. As shown in this structural comparison, a symphysis utilizes a robust pad of fibrocartilage. This tissue permits a slight degree of compression and movement. We see this mechanical setup at the pubic symphysis, between the vertebrae, and at the manubriosternal joint. While cartilage provides some developmental utility and a degree of shock absorption, the structural lack of an internal void prevents these joints from achieving true, free articulation. To achieve full, unrestricted movement, the skeleton requires a mechanical departure from solid connections. The bones must physically separate to create negative space. This defined negative space is the synovial cavity. Its presence is the defining characteristic of our third and final structural class, synovial joints. Maintaining this empty space requires dedicated architecture. First, articular cartilage caps protect the bone ends. Next, an outer fibrous capsule wraps the gap. Inside, a synovial membrane secretes fluid to lubricate the joint. Finally, dense exterior ligaments reinforce the structure. Once this standardized cavity and capsule architecture is established, the trajectory of the joint's movement is dictated by the physical geometry of the bone ends. Looking at the source, geometry dictates function. We see plane joints between carpal bones, hinge joints at the elbow, and pivot joints in the neck. Further down, highly mobile geometries appear: condylar joints, saddle joints, and maximum mobility ball and socket joints. The introduction of a fluid-filled cavity forces a strict biomechanical trade-off. Synovial joints sacrifice the extreme inherent stability found in cranial sutures in order to achieve free, multi-axial movement. Because mobility is tied to structure, medical professionals overlay a secondary, functional classification system onto this matrix, categorized by the degree of movement allowed. The first functional category is synarthrosis, defined as an entirely immovable joint. Function maps to structure. Synarthrosis correspond directly to the tightly bound fibrous joints, like the sutures of the skull. The second functional category is amphiarthrosis, denoting a slightly movable joint. These align with the compressible but cavity-free secondary cartilaginous joints, such as the pubic symphysis. This document lists the third and final category as diarthrosis, defined simply as a freely movable joint. This functional label applies exclusively to the synovial joint classification, where the dedicated cavity allows for unhindered articulation. Structural anatomy and physiological function are mathematically linked. The precise combination of physical binding tissue and internal cavity space dictates the exact inverse relationship between human skeletal stability and mobility.